Maths is all about the use of symbols and numbers. When we're working with mathematics, we use symbols to represent quantities and numbers that we're then able to manipulate and work with to carry out the calculations and the processes that we are looking to do. Now we have to figure out an effective way to represent these numbers using symbols so that they're easy to interpret and work with, but they're also consistent. It leads us into the topic of number bases. Now, number bases are mathematical systems which we use to represent numbers, and they represent numbers using a specific set of symbols and rules. These symbols and rules determine how many symbols are used, and the value of each symbol is based upon the position it occupies within the number itself. And I'm going to demonstrate what I mean to you in just a moment. Now, a variety of number bases exist in the world and are used for a variety of different purposes. Base 10 is what's known as the decimal system. This is the default system for everyday arithmetic and mathematics. Base 2 system is called the binary system. This is particularly prudent in computer programming, where a lot of programming is done using ones and zeros. Base 8 is what's called the octal system. Now this has historical uses in the UK language system, which is a primeval language system from California, and the Paymian languages in Mexico, as well as in computing systems such as UNIVAC and IBM mainframes. And base 16 is what's called the hexadecimal systems. Now this is commonly used by humans to help process long binary sequences much easier and quicker. Now number bases are denoted using subscript notation. So for example, 1031 with a little 4 is 1031 and it's in base 4. Now as I mentioned before, base 10 is a common number system we use every single day. Each digit's position represents a power of 10, which can then be combined to make the original number. So if we think about it, 10 to the power of 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the power of 3 is 1000. What we're able to do is take the numbers that make up something in base 10 and then represent it using these powers. So for example, 365 in base 10. If I equate that in terms of positions to being in base 10, what that's telling me is the 5 lies in the 10 to the power of 0. The 10 to the power of 1 is where my 6 lies. And the 10 squared is where my 3 lies. And it's telling me I'm using a combination of each of these. What it's essentially telling me I'm doing is that I'm taking 3 of the 10 squareds, adding on 6 of the 10 to the power of 1s, and adding on 5 of the 10 to the power of 0s. So what I've essentially got here is 300 plus 60 plus 5, so the number 365. So I'm using powers of 10 to represent that number. That is the basis of the common number system we use every single day. Now we're able to convert between number systems using a set of steps which I'm going to demonstrate to you now. Now let's imagine I'm going to work in non-base 10 number systems for a moment, and I want to turn these number systems into base 10. So I want to convert a number from bases 1 to 9 into a base 10 system. What we do is we convert each corresponding power by the digit in the number from left to right, then we sum up the results. So what do I mean? Well, let's imagine I've got the number 1011 with base 2. What that essentially means is I'm going to look at corresponding powers of 2. So I've got 2 to the power of 0, 2 to the power of 1, 2 squared, 2 cubed, and each digit represents how many I take of each of these corresponding powers and how many I'm going to combine and add up. So what this is telling me is that I've got 1 of the 2 cubes plus 0 of the 2 squareds plus 1 of the 2 to the power of 1s plus 1 of the 2 to the power of 0s. So essentially what I've got there is 8 plus 2 plus 1, so I've got 11. So that number there, 1011 base 2, is actually representing the number 11 in our base 10 system that we use. Similarly, 212 to the base 3 can be done the exact same sort of way, using corresponding powers, but this time, because the base is 3, it's to the power of 3. Each of the digits again represents how many of that position we take. So 212 to the base 3 can be calculated using this system here. So I've then got 2 times 3 squared plus 1 times 3 to the power of 1 plus 2 times 3 to the power of 0. So in this case I've got 3 squared, which is 9, 2 9s are 18. I've then got plus 1 of the 3's, and then plus 2 times 1, which is 2. So that is the equivalent of the number 23 in our base 10 number system. Imagine I've got 634 to the base 8. Well, again, it's all the corresponding powers of 8, so 8 to the power 0, 8 to the power 1, 8 squared, and then each of these tells me how many of each of those corresponding positions I take. So essentially, it's telling me I'm taking 6 of the 8 squareds, plus 3 of the 8 to the power of 1s, plus 4 of the 8 to the power of 0s. If I combine all that and do that calculation together, what I'll end up getting is 412. So that number, 634 to the base 8, is actually 412 in our base 10 conversion. Now, one thing I mentioned earlier is a hexadecimal system, where it was base 16. Now, we have number systems where our base exceeds 9. And if that's the case, what we have to do is make use of the alphabet in place of numbers. When we're doing this, we assign each letter a value based on its position in the alphabet. So for example, A would be 10, B would be 11, C would be 12, etc. And then we build the system up from there, and what we would do is come from our solution at that point. So let's imagine I've got A5 to the base 16. Well, what that means is I'm going to represent it as powers of 16, so 16 to the 0, 16 to the power of 1, and because it's A5, I have to put each of those digits in the corresponding position. So my 5 is going to be 16 to the 0, but A, we're going to represent it by 10. So what that then means is I've got 10 of 16 to the power of 1s, plus 5 of the 16 to the power of 0s. What that then means is I've got 10 times 16, so 160, plus 5 1s, so it's 165 in our base 10 number system. Similarly, this C46 to the base 12 is increasing powers of 12, so 12 to the 0, 12 to the 1, 12 squared, and then my C46, the 4 and 6 go in the corresponding columns, and C represents the number 12. So it's then going to go in there. So what that then means is I'm going to have 12 times 12 squared, plus 4 times 12 to the 1, plus 6 times 12 to the power of 0. That's going to give me my number, which means in the base 10 system that we've got, it's going to be equivalent of 1,782. Last example I've got up here for you very quickly is B3D to the base 15. Again, corresponding powers going up there. This time though, my B, my 3 and my D again represent different numbers. The 3 is fine, it goes in its column. I just need to figure out the values for the B and the D. Well, B is 11 from there, and the D is the next number in the system, which is 13. So using this information, I can say, fine, in the base 10 system, it's going to be 11 times 15 squared, plus 3 times 15 to the power of 1, plus 13 times 15 to the power of 0. So I'm going to get the joy of calculating all of that, and when I do, I end up getting the value 2,533. So that's me converted that number into the base 10 number system. However, let's ask ourselves the question about what happens if we go the opposite direction. Let's imagine I want to convert from base 10 numbers into non-base 10 numbers. Now this can be accomplished using a process similar to the Euclidean algorithm. However, the biggest difference is that instead of looking for the remainder to be 0, like when we're finding the greatest common divisor, we continue until the quotient is equal to 0. Then the remainders, read from top to bottom, give the numbers in our new base. So let me demonstrate what I mean with that. So let's have a look here and convert 25 into base 2. Well, as I've said, similarly to the Euclidean algorithm, I'm going to say I want 25 is equal to something times a quotient plus a remainder. Well, in this case, the quotient is going to start as our base. So 25 in this case is going to equal 12 times 2 plus a remainder of 1. We then go till we get to the next step. So in this case, I'm going to say fine, so 12 is equal to 6 times 2 plus a remainder of 0. Now, if this were the Euclidean algorithm, this is where I'd stop. However, it's not. What I'm going to do is I'm going to keep going. So I'm going to say 6 is equal to something times 2, because remember the base is continually being the quotient the whole way down. 3 times 2 plus a remainder again of 0. We continue to go. In this case, 3 is going to equal 1 times 2 plus a remainder, this time of 1. And then my final step, and I know it's the final step because I'm going to say 1 is equal to 0 times 2 plus 1. So my number 0 coming in as a quotient, that means I stop at that point. What it also then means is I now have my number, because if I start from here going up the way, I can say that I've got the number 11001, and that's a base 2. So what I'm actually able to say is that number 25 in base 10 converted to base 2 is 11001 to the base 2. If I were to then convert that number back into the base 10, as we would work with normally, I should get an answer of 25. Let's have a look at another example here. So let's have a look at the example of 275 as a base 8 number. So again, I'm going to follow the similar steps. I'm going to have 275 equals something times 8 plus a remainder. So 275 equals something times 8 plus a remainder. Well, in this case, it's going to be 34 times 8 plus a remainder, which in this case is 3. I'm then going to continue on and go to the next step. I'm then going to say 34 then is got to equal something times 8 plus a remainder. Well, in this case, 34 is equal to 4 times 8 plus a 2. So I then go the next step further. What I want to say is 4 is going to equal something times 8 plus a remainder. Well, 4 is equal to 0 times 8 plus 4. Now at this stage, my quotient is equal to 0. So this is the stage at which I stop. I then look and I read up the way, and I'm able to say fine. So what that means is that it's equal to 423 to the base 8. So the number 275 converted to a base 8 number is 423 to the base 8. So similar to the Euclidean algorithm, we follow these steps and then make sure we can read it. We're fine at the end. And this is how we convert the number from a base 10 into a non-base 10 number. We can convert any number in our number system, which remember is default base 10, into another base number system. And as we said earlier, this has a huge variety of uses, from other languages to computing languages, encoding, all throughout our world. We have to be able to work with these in order to be able to expand our understanding of mathematics and be able to take things that we know here and apply them to different fields throughout the world to be able to develop and continually grow.